In this question, we're told there are 7 periods in Lilith's school. The number of late arrivals to her lessons for a random sample of 50 days is summarized in the table below. We're asked to use a chi-squared test at a 5% level of significance to investigate whether the above data can be modeled by a binomial distribution. Okay, so this is going to be a goodness of fit test. If you notice, we do not at the moment have a parameter for the binomial distribution. So we can set our hypotheses, but we won't be specific about the parameter. H0, the binomial distribution, is a good fit. H1, the binomial distribution, is not a good fit. We've been asked to test at the 5% level of significance. So alpha equals 0.05. From here, we're going to need to calculate the p-value ourselves. With the data that we have, we can find the average amount of lates that Lilith has within a particular day at school. So we're just going to find the mean from this table. We're just going to find x bar. Once we find x bar, that's the average amount of lates per school day. Well, there's 7 lessons, there's 7 periods per school day. So we're going to divide that by 7, and that will tell us the probability she's late to any individual lesson. So we're going to do x bar divided by n. X bar divided by 7. X bar is 1.86. Divided by 7, we get a probability of 0.269. This is the p, the probability that she's late for any individual lesson. This is the p that we'll use as a parameter in the binomial distribution. Okay, so let's just state the distribution. X follows a binomial where n is 7 and p is 0.269. Now that we've got that value of p, we can go ahead and calculate our expected values. The expected values are going to come from the binomial probability of 0, 1, 2, 3, 4, 5, 6, and 7 multiplied by the 50 days that we're considering. So in the first case, the probability that x equals 0 from this distribution multiplied by 50 gets us 5.577. And we'll just follow this through for each of them, and we get all of the expected frequencies. By the time I get down to 5, I want to be careful not to assume that this is where the expected values are going to end. For these 50 days, there weren't any days where Lilith was late to 6 periods or to 7 periods, but there is still some probability associated with those outcomes. So I'm just going to make an extra row here where the outcome is going to be 6 or more lates in a day, and the probability associated with that is actually quite small, but it does exist. It's 0.002. And the number of times that happened in these 50 days is 0, but it does still need to be included. As usual, we're going to look at these expected values and just ensure that they're all above 5. If not, we're going to need to do some merging. So the bottom 3 are all below 5, and even if we merge them, it wouldn't be big enough. So we do need to merge all 4 of these together. We're going to group these all together and use that to calculate our test statistic. So I'm just going to draw a table to summarize these outcomes. I have 0, 1, 2, and 3 plus, 3 or more. The observed values, 7, 4, and 3 are going to be merged together to get 14. And these highlighted expected values, when we merge those together, we get 14.198. Okay. Now we're ready to calculate the test statistic, but before I have that, I would like to get the critical value so I can make an immediate comparison. Our degrees of freedom, we have 4 rows here, so we're going to start with 4 minus 1, and then we also had to estimate our own parameter, so we subtract another 1. That gives us 2 degrees of freedom. Our critical value, we'll look this up in the tables, for 2 degrees of freedom at a 5% significance level is 5.991. Let's just look at this on a diagram. Any test statistic that is in this shaded region, any test statistic in this critical region, we are going to reject H0. So let's calculate our test statistic. I'm going to use the sum of the observed squareds over the expecteds and subtract n. So that's going to be the black frequency squared over the red expectation, or the red expected frequency. So I'll do this for all 4 of these rows, and then I need to subtract 50 at the end. And that gets us a test statistic of 1.282. Is this a significant result? Looking at the diagram, this is actually over here on the left-hand side. This is not a significant result. Okay, let's just formalize this. 1.282 is less than 5.991. It's not significant, and we'll finish with our 2 standard conclusions. One mathematical, saying there is not enough evidence to reject H0, and the other in context, saying there is evidence that the binomial distribution is a good fit.